Hey guys, welcome back. Let's talk about concepts and their measurements. So, concepts express common elements in the world to which we give a name. And so that's the definition by Breiman and Kramer. And hypotheses specify relations between concepts. So, when we talk about operationalization, a concept needs to be operationally defined in order to be systematically researched. So an operational definition specifies the procedures, operations that will permit differences between individuals in respect of the concepts concerned to be precisely specified. So what we're in reality talking about here is measurement. That is the assignment of numbers to the units of analysis, be they people, organizations, or nations to which a concept refers. Now, I really want to drive home the importance of operationalization and thinking about measurements and your measures because they're fundamental to how we draw inferences or conclusions from the data that we see based on these measures. And too often I see that there's not a lot of thought given into, well, what could be the influence in how we define this measure and the conclusions that we make as a result of that definition. And so here's an example of a paper I did that was a review of menopause nomenclature. It's a fancy word for essentially saying the definitions associated with menopause. So how did people in studies define premenopausal women and how did they define postmenopausal women? And what I found, this has been defining these constructs in themselves has been a complex endeavor. And this paper sort of goes through the history of that process. But really the most rigorous definition or standard has been the straw criteria, which is the stages of reproductive aging workshop, where they got the best researchers together in the field. They came together and they work through what the definitions of the stages of reproductive aging in women would be. And so that's what produced the definitions for postmenopausal women and premenopausal women. And in this paper, I was interested in not only the history, but also how much were people adhering to these definitions that were there. And what I found was actually there were major inconsistencies relating to premenopausal definition, which were, it could have been a lack of reporting. People just assumed people understood what premenopause meant, and so they didn't even define it within the paper. And it could have been that different people use different age brackets or age ranges to define premenopause. Similarly for postmenopause, there were some inconsistencies there. And so really, the key the finding revealed that there's a significant amount of heterogeneity, so differences in ways people define premenopause compared with postmenopause. And so I produced some recommendations and suggestions for this, including the fact that it should be transparently operationalized premenopause, and provided suggestions for how this could occur. Why is this important? Well, if you're investigating studies and you use a specific definition to categorize a group of people, then the results will be in some ways influenced by, or perhaps modified by, the ways in which you categorize people. And so here is an example of this again in terms of education and dementia risk. It's the association between low education and risk of dementia is quite strong and is supported in this paper as well. But what isn't as consistent is the definition used to define low education. So I would ask you to reflect on yourself as to how would you define low education? If you were a researcher, think about what do you think is the most appropriate definition? And assuming you pause the video and then restart it, what these researchers found, where they investigated, they systematically reviewed the literature to identify all studies that looked at low education and dementia risk, and they found that people defined low education anywhere from 0 years, so no education, to up to 12 years of education. And so in all of these results that we see where people were looking at the effects of low education on dementia, it actually encompassed this quite wide range of educational experience and opportunity, which may reflect different backgrounds and experiences of the people who reflect in those numbers. And so what I want you to take away from these two examples is nothing is a given in science. And just because a measure such as education or definitions of menopause, just because they're used by a study, doesn't necessarily mean they're used consistently by all studies, nor does it mean that they have a similar effect that can be seen irrespective of what definition is used. More often than not, the ways in which we operationalize constructs matters for the ways in which we interpret results. In an ideal world, people would use their definition and run their analyses and conduct their study, run their analyses, interpret their results, and their conclusions would be tempered within the scope of their definition. So there wouldn't be this broad sweeping, for example, in this education example, they wouldn't be saying low education in a study that had people from say 10 years plus. They wouldn't be saying those results applied to people with low education in brackets less than 10 years. However, that's not the case. And many people, when they have a definition and they categorize it, they'll apply it more broadly in conclusions. And I think that nuance is really important, and it all comes down to operationalization. So it might not be the most attractive concept out there, but I think it's really important for how things work. And you'll see some real world examples of this in action. You've already seen two of how these operationalization of constructs is critical. So another definition of operationalization is the act of making a fuzzy concept measurable. So social science often uses multi-item measures to assess related but distinct aspects of a fuzzy concept. And so what I want to emphasize here is the differences between fuzzy versus not fuzzy constructs. So you have fuzzy constructs, psychological constructs, including measured using the average or a composite score of a number of correlated items. So examples include felt emotions, perceptions, and attitudes. And not fuzzy constructs can be measured objectively and directly. So you can think of things such as physiological responses to emotions. So you have your heart rate, or physical properties, so height and time. These are constructs that can be measured quite objectively, whereas fuzzy constructs are those that rely on this sort of self-report. So they're a bit more, they're more subjective in their measurement. Now, the world is not black and white, as I've already emphasized, when it comes to statistics, and particularly when it comes to measurement. So there's nuanced constructs. So, for example, date of symptom onset for dementia. Is this a fuzzy construct or not fuzzy construct? Have a think about it, pause the video, come back. So when it comes to the date of symptom onset for dementia, we have to think about the condition itself. So dementia, most people think of it as Alzheimer's disease, so we'll use that as a example, but there's many other types of dementia. But for Alzheimer's disease, one of the earliest symptoms of Alzheimer's disease is memory impairments. And so people have difficulty with their memory. And so when you ask someone who has Alzheimer's disease the date of symptom onset for dementia, already there's some error that's introduced there. But you may say, well, you could sort of address that by having their carer or partner report the date of symptom onset. And that's a good idea. But the problem that comes with that measurement is inherent within the disease course. Someone doesn't wake up one day and then start experiencing memory problems. The disease is described as something called insidious, which means that it has a slow progressive onset. So the changes happen slowly over time. And so for someone to pinpoint the date of symptom onset, it's very difficult to do. And so, which is understandable given the nature of the symptoms that's experienced in the condition. And so the question that I had was, how were researchers addressing this? degree of missingness that would inherently happen. When I looked at a data set in a paper that was looking at diagnostic timelines, I found that there was a degree of missingness that was there for the month of symptom onset reporting. So while people may have known the year, they may have said, oh, back in 2016, I started to experience some symptoms. I'm not really sure of the month. Then the month was unknown, but the year was known, and that's typical. But what I noticed is many studies, they treated the measure as a very precise measure, which for the reasons I've articulated, wouldn't be expected. And so what I'm interested in investigating is what are the degrees of missingness in papers that are reporting date of symptom onset, and how is this addressed by researchers, or how could it be addressed? Because all of this has really important implications for, if we say, how long it takes to get a diagnosis. Well, that starts with the date of symptom onset for dementia, time that you have symptoms to time to diagnosis, or time to when people die from having dementia. And so that model is influenced by time from symptom starting, or time till when people experience their first GP visit, right, in relation to these symptoms. And so again, so all of these really important measures that we use to make assessments of how our healthcare system is performing, how people's experiences with dementia may vary across different systems. All of this is informed by the date of symptom onset. And so that's another construct. Well, is it fuzzy? Is it not fuzzy? Well, it's relying on self-report, but there is a true day. There are days that could be there. It may not be recalled, may not be remembered correctly. There's likely some months there in which those symptom onset occurred, but it may not be remembered. And so that's the nuance within constructs. So they could be, so you can think of that as the scale of fuzzy, self-reported, or perceptions of attitudes, felt emotions, then non-fuzzy, which is directly measuring objective constructs, and then this nuanced middle ground of mid fuzzy. I didn't think that doesn't sound so good. So I think nuanced construct is a better term. Excellent. So how do we go through the process of operationalization? So what are the steps to take? Well, in some ways, through my story of the menopause and nomenclature paper, you have a sense of how that happened in that construct, right? When they got the greatest minds in the field together for a workshop to try to come up with definitions, and they go back and forth with what they think would be the best definitions. So that really is the brainstorming the indicators of a concept and defining the concept and drafting measurement items. Those could be done within something like that sort of setup. And then you can progress to pre-testing and pilot testing your measures, examining psychometric properties, so how precise are these measures, and then you redraft, refine, and retest measures. So the process of measurement operationalization is a difficult one, and should always be scrutinized when you have a measure. So just because a measure is in existence in the literature and it's been around for a long time, we should always be considering, well, how did this measure come to be, particularly if it's based on a fuzzy construct, and are there ways in which we can improve upon this measure? So the exception is in this whole process, I mean, for operationalization, if a measure already exists for a construct you're measuring, you start from that measure and see how can we improve it. You don't redo this whole process every time you want to update a measure. So that is everything about operationalization. Now what we're going to talk about is measurement noise or measurement error. And there's a great book by Daniel Kahneman called Noise. So I'd highly encourage you read it. Actually, I think I found the blurb for it. Yeah, excellent. So it's called Noise, a Flaw in Human Judgment. And I think the blurb is great because it gives you a sort of a high-level overview of what noise is before we go into the statistics of it. So it says, imagine that two doctors in the same city are given different diagnoses to identical patients, or that two judges in the same courthouse give markedly different sentences to people who have committed the same crime. Suppose that different interviewers at the same firm make different decisions about indistinguishable job applicants, or that when a company is handling customer complaints, the resolution depends on who happens to answer the phone. Now imagine that the same doctor and the same judge and the same interviewer or the same customer service agent makes different decisions depending on whether it is morning or afternoon or Monday rather than Wednesday. These are examples of noise, variability in judgments that should be identical, right? So that's really the framing that I want you to go in with thinking. A great book, highly recommend you read if you're interested in learning more about noise and its application in real world environments and how it can influence decisions. But within the context of what we're talking about today, it's all about imagining that you have an observed score, and in an ideal world, that's representing the true score. But in reality, we know that there's some degree of measurement error that's occurring. So our observed score is the true score plus measurement error that's occurring. So measurement error is the statistical deviation from the true value caused by the measurement procedure. And so it can be random or it can be systematic. So the random error is you have this systematic error plus or minus random error. And systematic error is where you have sampling error plus or minus non-sampling error. And we'll go through this in more detail in a moment, so don't worry. The main thing I want you to gather from this slide is that you have every observed value you have in your data set, it's based on a measurement, ideally if your construct is and your measures are measuring what they intend to measure, it's based on the true score and measure plus or minus measurement error, which can be random or systematic, right? So that's the main takeaway. Hopefully that blurb emphasizes what noise is in a good sense there. So what are sources of systematic error? So it could be non-sampling or sampling related. Non-sampling systematic error can be test reliability and validity, and we'll talk about these constructs in a moment for this lecture. It could be respondent bias, for example, social desirability. What I mean by that is, say you're asking people how much they eat in a week, which we know people typically tend to underreport how much they eat in a week, and this is why we use food diaries to help with that process. Or if you ask them how much they exercise, typically people overestimate how much they exercise in a week. And so this in part is the social desirability. They're providing responses that allow them to be more desirable, that are more desirable socially, or allow them to meet expectations. There's the researcher bias. So it could be, for example, conscious or unconscious bias that can occur. So in many cases, it can be a researcher is designing a study and they have read the literature, they're really certain as to what they expect should happen, and in some ways they may unconsciously or consciously influence the result as a function of that, because they're attached to hypotheses. The most important thing in research to do is to have humility, to understand your hypotheses are not you. They are simply your best guess based on available evidence, and your ability to update those guesses based on the evidence is what will make you a robust researcher, which is why, circling back to the first lecture, I like Bayesian frameworks, because it embedded within it is that process of constant updating based on what the data says and what your prior beliefs are, and then you use that combination to influence what you take forward as to what your beliefs would be in the model. And so it's an important lesson in research, but also something to keep in mind in terms of our own biases, what we're aware of and trying to mitigate that, and also not. And this is why we try to design studies to mitigate this where possible. For example, we have double-blinded randomized control trials, and this is where in the process, the patient, for example, imagine we're administering a drug and it's a treatment drug for Alzheimer's disease, and you have all sorts of patients. They get randomized into treatment group and placebo group. So the patients may not know whether they get the drug or not. And then the person administering the drug, they may not know whether they give the drug or not, because there's all sorts of conscious and unconscious bias that can occur. If the administrator knows that who's getting the drug, they may be more careful in how they administer, and it can unduly influence the results. So there's researcher bias is good to be aware of, but also we try to design out where possible. And then also paradigms that can influence it. For example, assumptions that people have, the focus on positivism, and collection methods. So all of these factors can influence systematic error. And in terms of sampling error, this could be non-representativeness of the sample, which can produce that systematic error that you see, because you're skewing the data based on the sample that you have. So the systematic versus random error examples. So in terms of a high level example to get a sense of it. So a systematic error is where, for example, you step on the scales and they're not calibrated properly, but every measurement that you get is always 50 grams too high. And so this same error occurs for each measurement. So that's why it's systematic. And so that's why you can see in the previous example, sampling is a systematic error, because you have a sample where you're getting similar responses, but they're perhaps not representative. They're not representative of the target population within your sample. And so random error, this is where you measure the same cup of flour 3 times and get 3 slightly different readings. So the amount of error differs for each measurement. So in systematic error, you're getting the same difference each time you're measuring. Random error, the amount of error differs for each measurement. So then let's come to measurement precision and noise. So the lower the measurement precision, the more participants are needed to make up for the noise in the measurements. So the more participants you have, the more precise you can get with your estimates. But even with larger samples, noisy data can be very, very hard to interpret, and it's a real challenge. Especially when testing and assessing individual clients, special care is needed when interpreting results of noisy tests. So if our job as statisticians is to acknowledge noise in our interpretation of results. I was reviewing a paper a while ago, and they had done their regression models. They had looked at everything, but fundamentally, when they look at your R-squared value, the coefficient of determination, it was 0.0 something, right? So they were interpreting all these effects, but the R-squared value was so small. I said, what does this result mean in the context where 99% of the variance is unaccounted for or unexplained, right? And when we're creating models in statistics, we want to be able to address the variance that's occurring and also noise and measurement. And so these are important concepts to consider, because if you get too much in the weeds, you don't step back and say, well, what does this data mean, or what do these results mean in the context of the data and measurement precision? And so what we want to do is we want to minimize non-sampling measurement error. So we want to standardize administration conditions with clear instructions and questions, minimize potential demand characteristics, so you train your interviewers to prevent that, and use multiple indicators for fuzzy constructs where possible. So those are sort of the ways in which you can minimize non-sampling error. To minimize sampling measurement error, you want to obtain a representative sample, so use probability sampling if possible, and for non-probability sampling, you can use strategies to minimize selection bias. For example, you could say, I'm going to select people within this group, but I'm going to select every 3rd person or every 5th person. So that's some sort of sampling method that allows you to minimize that selection bias. You can maximize response rate. So you can do a pre-survey contact of the person, minimize the length, time, or hassle of the survey so that someone completes it. Really, that's probably my core focus when I'm conducting a survey, is how can I make sure that the survey is as short as needed to ensure that I get the data that I need for the analyses, but also to ensure that there's not a demand on the participant to complete a long, lengthy survey. Some cases it's unavoidable, but where it can be avoided, you get a big increase in participant completion for your survey. So you want to have rewards or incentivize people to complete your survey, but it's a balancing act. You don't want those incentives to drive certain responses. You want the incentives to be incentivizing, but not too incentivizing. You can use colored paper, which can be attractive, and also callbacks and reminders, which is a very effective tool, sending emails or calling people up and saying, hey, have you had a chance to complete the survey? To minimize measurement error, you can ensure administrative accuracy. So set up efficient coding with well-labeled variables. Check data, double check at least a portion of the data. There's this great story a colleague of mine told me where when he was a research assistant, he was employed to input a huge amount of data into an Excel spreadsheet. And someone came in, it was like a partner of someone who worked there. And he said, oh, what are you doing? And he said, oh, just getting this batch of surveys for today and I'm putting the data. And he said, but aren't those surveys, couldn't you actually run a computer program to do that? Do you have any software that can do that? And he said, oh, no, we just look at the survey that's been completed and we extract the data, put it in the Excel spreadsheet. He said, I think I could do that for you if you wanted. If you want to pay me for a bit of work, I could probably get that done for you and do all of this through a program. And the guy said, well, how long do you think it would take you to do the work? He said, probably a day to write this program. It shouldn't be too complex. He talked to the manager, they approved it, they hired him for a day, he wrote the program out, and it worked. He was able to transcribe all the survey data into an Excel spreadsheet in the format that they wanted to conduct their analysis. And so they wanted to check that the program worked correctly. So what they did is they went back on all of the human entered data and they checked whether it was inputted correctly. And they found some discrepancies. And when they went to check the discrepancies, they found that in all those cases, the humans had made an error in the inputting of data. And it may be, I think it's interesting because it shows you that you want to minimize error where possible. And in some way, for processes that are automated, there's a combined approach of using computer programs and humans can allow for that efficiency of data. And you may think to yourself, well, if I was doing this research, I wouldn't have any errors. I'd be very careful. But they had thousands of surveys that they needed to embed within a spreadsheet. And the manual labor that's required, it's almost expected to have some level of error. And so the checks and balances in place can be either using computer programs, which can be effective. But if you don't have that, you can check the data. And often at times, what I've done when I've done studies where I'm extracting data or collecting data and extracting it is I actually have someone double check all of the data extraction. And if that's too onerous, then you can double check a portion of the data. As much as the person can do is ideal as the guideline there. So psychometrics, the goal is to validly measure differences between individuals and groups in psychosocial qualities, such as attitudes and personality. So that's the goal of psychometrics. And the task is to develop approaches and procedures, so theory and practice, for measuring psychological phenomena. So you can design and test psychological measurement instrumentation. So for example, examine and improve reliability and validity of psychological tests. And the methods that we use are factor analysis, which you're well familiar with now, exploratory or confirmatory, or classical test theory, which is reliability and validity. So what we'll do is we'll take a break there, have a break, maybe check out Noise by Danielle Kahneman if you're interested, and have a reflection on what we've talked about so far. Stretch your legs, grab a tea, we'll get back and talk all about reliability and validity. So I'll see you guys very soon.